Alrighty. Yeah, thanks for coming. To our final review session or workshop here. We're going to be talking about fault tolerance and security. Alrighty. This is the event code. Do you want it or it's a
ACM membership.
yeah. Okay. Alrighty. So these are the topics we're going to be touching upon. So fault tolerance and failures, and then talking through process resilience and access, which Daniel is going to do, and then reliable communication, secure communication, and then authorization at the end. Cool. So let's talk a little bit about some of the unique failures that can occur with a distributed system. So yeah, we have a new notion of like a partial failure here, where part of our distributed system is failing, but the rest of it is still working. So we need to write our software to be able to identify that and recover from it. Um, so an example of kind of some of the ways that you can have a partial failure relate to different dependability metrics here that I've listed on the side. Just to kind of illustrate these through an example, if we take Amazon's S3 service, which is basically just a like you can store like any binary encoded file, so it's like a blob storage service. Um, they achieve availability through um, basically allowing people to have direct access to the content anywhere in the world. Um, Reliability through whatever metric, whatever kind of percentage guarantee that they can give you that your data will not be corrupted and not be lost. I think it's like 99.999 something. Um, and then safety through making sure that nobody can access your data if you want it encrypted, um, that kind of thing. And then maintainability corresponds to the guarantees that they can give you for recovering your data or recovering, well, in terms of S3, it'd be recovering your data, but more broadly, in terms of recovering from that kind of partial failure if you encounter one. Cool. So I've listed some failures here. The names are on the left, and on the right we have the definitions hidden. Hold on a second. I think this is ended. Let's see. Hello? Okay, give me 1 second. Do you want to forget it? Yeah, just take that. Okay. So yeah. Do you want to try to take a stab at guessing what a crash failure is?
Uh, like this, like randomly published, I guess.
Sure, yeah, I think that would be an example of it.
But yeah,
Basically,
it's not like
yeah. So I think the um, yeah, basically what you just said, right? It just suddenly stops working, um, but it's working up until that point. An omission failure is basically corresponds to a scenario where we don't have data which we expect to have. So there's two different types of an omission failure. So yeah, obviously this can happen when you're trying to send a message and maybe you don't include certain parts of the data or for whatever you can't like think you sent the message but didn't actually send it. And then same thing for receiving. Um, and then a timing failure is pretty related to those two, but slightly different. So it's when basically you may receive the response or something like that, but it's like outside of the expected time interval, so you don't process it as you would expect to. And then for response failure, we have um, kind of two types. So this one here, the value failure, corresponds to when your response is coherent, but it's not what you expect. So maybe like it's supposed to have the next ID number, like you're sending one responses there and back. It's supposed to have the next one in like this series, I guess. But for whatever reason, it skipped a number, even though it's coherent. If the value's not right. And then state transition failure is when basically the response itself is corrupted, doesn't have the correct data. So maybe you do something that you're not expecting to do that causes kind of like subsequent problems. And then an arbitrary failure is when basically you don't know what's happening at all, but there's some sort of failure. Okay, cool. So kind of trying to add that. Okay, thanks, Thomas. Trying to talk about these failures in terms of our very simple kind of calculator model that we had. We've been working with way back when. So we can see that we would experience a timing failure here when we're actually sending a message. If, for example, we use an UDP maybe, and then the packet is lost with TCP and we'll drop in connections not stable. we may receive an omission failure, either when sending or receiving a message here, and then the response failure would happen at the receiver there, depending on what the status of the actual data is. I think everybody get the box. Okay. But yeah, we'll get to that. Okay, cool. So beyond those types of failures, we can also experience, well, when considering the failures, we want to consider how our actual code is running on the different nodes of our distributed system. So as we've talked about before, there's a notion of running processes synchronously and then running them asynchronously. And generally with distributed systems, as we've talked about, you'll want to opt for asynchronously doing that. But the issue with that is that you can't use timeouts in like the traditional way that you would expect to. Because if you're running processes asynchronously, the time to complete that, whatever task you have, is not necessarily fixed, meaning you can't be as sure whether your process has failed or it's just kind of still working, maybe in the background or something like that. That kind of leads us to this notion of a partially synchronous system, where we kind of have a timeout, but it's an extended timeout, so that we can try to account best we can for the asynchronous nature, but we're still kind of giving a sense of synchronicity so that if it times out, we can treat it as a failure and then move forward from there. Okay, so here I've listed some of the different types of failures that we would experience in a system, assuming it's partially synchronous. So yeah, we have a notion of fail stop, which is basically where the failure can be reliably detected. And we're going to go through a couple examples of all of these in a second. So generally, this requires you to have a reliable connection so that you can actually actually reliably hear back from the server or reliably know in some way, right, that it's not responding. We have the notion of fail noisy, which is basically where at some point we can know that there was a failure, but we may not know initially, and we may kind of continue trying to process for a short while. We have the notion of fail safe, where there was a failure, but it was handled generally at the receiver side, the server side, so that it's like benign and we can continue working fine. Fail silent, where we're unable to distinguish between a crash and like an omission failure. And then we have fail arbitrary, where failures are not detectable at all across the connection. So, and I'll share an example of this later as well. Okay. So yeah, and then just getting through some more of the introductory stuff here. So one of the ways that we can try to mitigate these failures, at least the failures through omission and value failures, or through masking. So sorry, through redundancy. So one way that's done is through kind of including parity bits or just data redundancy, other data redundancy metrics, or I guess, well, not metrics, data redundancy tools, I guess. So generally this would lengthen the payload of the data, but it would allow us to kind of recover if a couple of bits are corrupted, that kind of thing, or at least detect that they're corrupted. And then beyond information redundancy, which is adding this additional kind of extending the payload, but adding the additional ways to recover the data. There's also a notion of time redundancy, where basically in the time domain, we're redundantly adding, a message. So for example, a common example of this would be if we're just sending the request again, right? Even if it's handled by the server, maybe we don't know if it is or not. Right? So to be more reliable, we can just send the message. And then physical redundancy. So this is more in terms of like if you have something that's like processing data, for example, that's hosting a website. You probably want to have that on multiple nodes in case your main node fails, so that users on your website can still access the website without any issues. And that's an example of physical redundancy. Okay, cool. So let me pass this off to Daniel.
Process resilience. Okay, so we can have something called a process group, which is basically just a bunch of identical processes running at the same time. And these provide a fail-safe. So basically, if one of our processes goes down, we have the rest of the nodes in the process group that can basically just handle the request And so from the outside looking in, this process group will behave identically to a single process. Outside observers will not know that there are replicas inside the process group. There are two ways to organize these process groups. So we have a hierarchical architecture and a flat architecture. So for a hierarchical architecture, it's much simpler. There's less communication overhead in order to manage this. So for example, on the one on the right, it's a hierarchical architecture. You basically just have one node coordinating everything and a bunch of workers that are processing all the requests. However, this runs into the same issue as like not having a process group. So one way we can have a hierarchical architecture is basically, we just pick one process to be the leader and just have everyone else follow. However, if a leader goes down, it's kind of screwed. You have to find a new way to choose a new leader, which can cause unexpected delays. In a flat architecture, there's many more connections, so that's another source of overhead. However, it's much more fault tolerant than a hierarchical organization. And so if one of the nodes in the flat architecture goes down, it's not too much of an issue since all the rest are directly connected with each other and can continue on. And another issue that we need to consider is exactly do we admit new processes into each process group, and how do we make sure that all the nodes know that when a process leaves the group? And so there's three ways we do this. So one is we detect when a process leaves, and so this could either be cleanly with like a formal message send, or maybe the process can't send the message because it crashed, right? So we have to figure out a way to do that. Another way is multicasting. So you basically just have a client multicast to a bunch of processes, and then they handle it from there. And so this is a diagram where it's basically like, the client sends a message to three of these nodes in the process group. And then, maybe one leaves, one fails, you still have one that can handle the request. Okay, so one way that we can have the nodes in a process group come to a decision about what action to take is through a flooding consensus algorithm. And so basically it relies on a fail-stop model, which means that all failures can be cleanly detected and you have a reliable source of communication. So basically the first thing that happens is that your client sends a list of commands to all the processes, or actually no, the node in the process group sends a list of commands to every other node in the group. And so another requirement for this algorithm to work is that it's deterministic for the final action that the process is going to take. So for example, if you have an identical set of lists of actions, then you're going to reach the same conclusion as everyone on all the other processes. And so basically one is broadcasting the list of commands, and then you merge all the results. And after you receive all the results, you decide what to do. However, some problems that can occur are basically crashes, right? So in this first process, we see that not all of the messages have been sent out by process one. Basically see that, process 2 and 3 do not have process 1's list of proposed actions. However, process 2 does have the entire list, and so they can do a decide message over here and propagate that to the rest of the processes that have not crashed. Another problem is that, like maybe let's say it sent out a decide message to process 3. However, it does not send it to process 4 because it crashed before sending it to process 4. In that case, you basically just have process 4 still waiting on the first round. However, process 3 can continue on and proceed with round 3 and round 4, which could lead to a sort of like disconnect in the process states. So another more resilient algorithm is called Paxos, and so it does not have the same rigid requirements or assumptions that the flooding consensus algorithm has. So this algorithm basically relies on 3 axioms. So we assume that all our nodes are partially synchronous. That means within the process it's like synchronous. However, among them it's like not necessarily. We also don't have any arbitrary failures, and it's also round-based commits. So in this diagram, we basically have each process separated into three sort of broad tasks. So this is like a single server process. However, we also have like composer, acceptor, and learner. So each process would basically split its task up logically. However, it's not actually three separate processes. It's like one process doing all of these things. The first phase is like when a proposer receives a client. It basically just forward all the messages to all the acceptors. However, the way that it does this is actually kind of special. It uses Lamport logical times, or uses Lamport logical clocks, which is basically a way of timestamping messages such that essentially if an event happens after another event in the same process, you're guaranteed to have a later timestamp, but there's no guarantee for events between processes. The reason we want to do this is so that events are processed in order so that if that happens in one process, then it's like causally linked. However, between processes, it's like doesn't really matter that much. And so basically, you would send a prepare message, and then not to get too much in the weeds, but yeah, you adjust the internal time clock of each process to match the assumption of the vector time of the Manfort's logical clocks. And you either accept the the acceptor promises the proposer that essentially it's not going to accept any other proposals with a lower timestamp than the accepted proposal. After that, you just basically just accept it after you accept the proposal after each of the acceptors has promised that it's not going to accept any new proposals, and then you send it to the learner, which actually executes the action. So essentially, this is just a complicated way of doing a two-step commit. Is the main takeaway from that. Okay.
All right, so now let's talk a little about how reliable communication is actually effective. Okay, so I don't know what there's a space there, but here we have a couple of examples of different kind of point-to-point failures that one might experience. So the first thing we're going to do is just kind of classify them with those five kind of fail categories there. So yeah, if the client is unable to locate the server, what kind of failure do you guys think that would be? Noisy? Okay, that's a good guess. I think honestly, I feel like it could be classified as that. I have it down as a failed stop, because you can identify, like you will get that specific response back depending on like, I mean, the question's a little vague, right? Like if, for example, the server doesn't exist, ideally you would get that response back in a fixed, like amount of time. Generally with noisy, you can't estimate the amount of time, and you can't put an upper bound on the amount of time that you would need to take to know for sure that you fail. But with fail stop you can, which in this case you would be able to. All right. So another scenario here is if the message from a client to the server is lost. So I think this one I have down. Oh, okay. I have it as failed stop, but I feel like failed noisy would also be a valid response for that. And then if the server crashes after receiving a request, what would that be? So the server does not reply. Silent. I think that's right. Yes. Okay. Awesome. Yep. So basically, the client will just keep retrying, right, to try to hit the server, but obviously, the server's dead. Okay. Okay. So yeah, I've listed here a couple of different approaches that the client might take. Generally, you're going to run with this keep trying this server so at least one semantic. But yeah, there are different approaches the client could take. Okay. And then what if the server does reply to the client, but the message is lost? What kind of failure would that? Um, no, I don't actually remember off the top of my head. I think it's fail noisy. Yeah, okay. The reason why is because for the time being, like initially, for example, maybe you're I can't think of a great example off the top of my head, but the general kind of scenario where it'd be noisy is if you're sending data, and you have maybe a long timeout or something, like, and then you keep sending data, so you're expecting the server to have like received your first message, right? So for the time being, everything appears fine, but then eventually you'll realize, oh yeah, I didn't, like, or the server didn't get that message, right? Um, and then if the client crashes after sending a request, is there a way for the server to know that if the client is still alive, generally? Yeah, generally it's going to be fail arbitrary, right? Because um, the server doesn't, so like if I send a request, right, and then the server tries to send me a response, generally the server doesn't know whether the client is like I could send like type in something in my browser search and then immediately close my browser, like shut down my laptop or like destroy my laptop, right? The server doesn't really have a way to know. The server doesn't really have a way to distinguish between me just like sitting idly, um, and me like closing my browser. Uh, like it doesn't unless I send that closing request. So it kind of depends on the implementation, but generally this will be a fail arbitrary set, right? That makes sense? Okay, cool. So then now let's touch a little bit on reliable communication in like a group setting. So this is something similar to the scenario Daniel was mentioning, what we're mentioning. So yeah, generally what we'll see is that we're going to have a single sender or maybe a couple senders and then a lot of receivers. So we want to make sure that the receivers are able to receive consistent data and receive the data reliably. So generally this is implemented through a bunch of like kind of point-to-point communication. So maybe the server would open up 4 connections here, one to each node, and then send the data through some sort of reliable means, probably TCP. And then it'll do that in parallel. Um, yeah, I think some of the key ways that you're able to ensure that the data is consistent with each other is by doing what's known as a distributed commit. So this diagram here kind of illustrates what that process would look like. Essentially, what you need to know is that each of the kind of nodes that are going to be doing the commit need to vote depending on whether they can actually handle it. So the coordinate node, the server here, will kind of go into this initial state, and then it will signal. So when it's initializing, it will signal all the participants that they need to vote. And then the participants, they will actually vote when they're initialized. The coordinator will get all the votes, make a decision, and then announce it. And then here, depending on if it's vote commit or vote abort, it'll abort. So nothing, not too tricky there. It's pretty straightforward. Um, yeah, and then the other thing here is that there's a notion of an atomic multitask where we're basically trying to say, we're writing this data out, and all 4 of my replicas need to have it at the same time. So generally, the way that would be done is, for example, if we're sending our data in packets, we would send a packet to each of our nodes. Each of the nodes would buffer it, and then we would get acknowledgements back. But for example, if this node wasn't able to get that packet, so we would resend the packet to this node. Once we get an acknowledgement, we can send out the next packet out, and then once the nodes get the next packet, then they know that that particular piece of data has already been written out. So they're good to kind of add it to their data store. That's the one.
Okay, so now how do we make sure that our communication is secure? So basically we have 4 different type of things that we implement inside a distributed system. So the first thing is our communication mechanism. So how exactly do we get data from one point to another? The next is authorization, which means how do we make sure that a party that is trying to access data actually has the permission to do that. And this basically protects us from interception, which means that if someone's like reading all our messages, interruption, which means that someone's like causing our system to go down, modification. So like no one can like change the data before it actually gets to the other point. the fabrication, so that no one can like kind of pretend to be us without some sort of detection. And so we're going to talk about how what sort of policies we need to implement and how exactly we're going to enforce those. So common security policy, we have an encryption scheme. Everyone knows what that is. But you just like jumble your data so no one else can read it. Authentication, which means that how do you know that someone is who they claim to be? Authorization, as you said, like permissions and stuff, and auditing. So if there is a breach, like how do we detect that? Okay, so here's an example of a security key authentication. So this is called public key authentication. It's basically just like use your public key to encrypt, and then the public key and private key are going to be like linked mathematically. So only the person with the private key to this recorded public key can actually solve the challenge that you're going to send. So essentially, it goes like person X sends a message to person Y, and you basically just, or actually, no, I messed it up. So person X is requesting person Y for something, and person Y needs to make sure that person X is who they say they are. And so it's gonna basically send over like a random challenge right to person Y. Is gonna encrypt that with its public key, and it's gonna send it back. And then did I mess up the order? Wait. Random number, encrypt it, decrypt, and yeah. So you encrypt it with your private key. This is ZX, and person X sends the decrypted version to person Y. If that's correct and it matches the initial number that's sent out, then that person X is valid, and person X does the same thing. Yeah, I think that's right. Okay, next is a key distribution. Oh,
This one.
okay.
So is K of Z Y?
Oh, let's see. Yeah, so you request the data, so that's X the request, and a person Y basically sends an encrypted number. Essentially just like picks a random number, encrypts it with the public key, and then sends it over. If person X is who they claim to be, it'll have a private key linked to the public key, and it'll basically just like decrypt that was KXYZY. That's like the decrypted version to person Y, and if it matches the like initial number that person Y has, then the person X will be verified.
What's ZY? What is 4 and 5?
Like 4 and 5. Yeah, so 4 is basically just an encrypted, it's basically just like person X verifying person Y.
Oh,
Yeah, so it's like a two-way thing. Okay, and so next we have a key distribution center. So since like that process is kind of complicated, you want to limit the number of times you have to do that. So essentially, if we have like n users, we might need like n different keys, or like n squared different key stores. For one, like you have basically user n has to like have a key for every single other user that is authorized in order to actually do a proper key exchange. However, if we want to narrow down that complexity, we can just have a centralized way to get public keys. That's like valid, vetted. It's like vetted, right? So we have a key distribution center is basically just where people go to get public keys of other authorized users. And essentially all you need is that if you're like a new user, you only need to know the public key of this key distribution center and then go to there after you like verify and then you can know that JDC is basically authenticated to be a valid source of public keys, right? It's not like a malicious attacker sending out fake public keys where all the like keys are just just the attacker, right? So this way you only need like n keys instead of n squared. Okay. And then this is like public key authentication, which is kind of what we went over. So like So this is a kind of a more clear picture, if all that like ZXKX stuff was a little messy. Right, so like, you have a public key that's like authorized, and that's each server checks if it's in the list of authorized keys. If a vacuum key is found, then it basically you encrypt a message with a public key, and then the client decrypts it with its private key, sends it over, and if that's valid with the MD5 hash, then yeah, then you have a secure connection.
Alrighty, so yeah, common use case for authenticating is authorization. So generally the three ways that that can be done, illustrated by the black kind of rectangle here. So yeah, essentially we can actually protect the output data itself. We can protect against unwanted kind of operations on the data, which is this one here, right? We were kind of protecting the like API kind of layer, so to speak, over the before the data. And then finally, we can actually kind of protect the data by limiting the users directly. So kind of some ways that that can be done, each of those can be done. We have this notion of an access control matrix, where basically it's essentially just a table of like, users and then kind of their permissions there. So generally this is stored independently of both the users and of the data itself. And kind of this might seem a little cumbersome, right? Because here what we have to do is for every file, we need to have all of these permissions listed. So kind of a simpler way that you may, a simpler form that you may see is by default, everyone that doesn't have any permissions. And then we have an access control list where basically, instead of this table being super long for every file, we essentially just have a linked list at the end for each user that lists all of their active permissions. And this can, instead of just being stored in like a table format, allows us to store it in at the actual objects themselves, right? For example, if I'm trying to do a read, we know where the actual object is in memory, so we can kind of go to that file and then check the access control list, make sure that I have whatever permissions I need, and then kind of give permissions. Okay, and then an alternative approach is to use what are known as capabilities. So these are basically stored at the users themselves and are essentially just a list of like the permissions that the user has. Cool. And then another way in distributed systems that we try to handle authorization is through what are known as firewalls. So yeah, there are a couple of different ways to do this, but like in their barest form, essentially what they're used for is just filtering communication. So if somebody's trying to access a server, we can filter that communication depending on where it's coming from and depending on what the contents are. So yeah, a very common use case for this that you'll see is what's known as a NAT gateway, where basically we have our kind of our internal network where we want our like gateway to communicate to our servers or whatever. But we don't necessarily want communication from the outside the internet to be contacting our internal servers and our internal database, like writing random stuff, right? So instead of to block that out, what we can do is we can kind of obfuscate the IP addresses of our internal servers and database by using a it's this one here, some sort of like internet gateway. So this is technically publicly accessible, but we can inspect the content here and like filter it out prior to actually getting to our internal servers and database to prevent that unwanted access. Yeah, and then the other thing is that we can also use these firewalls or like application gateways to do routing. So generally that would kind of be filtered to the same unit. Okay, cool. Yeah, so I think that's it for fault tolerance and security. If you guys had any questions, feel free to ask them. But yep.
For inspecting vendors, like they all need to start with one certain correct thing, or like they each have a different one?
Yeah, so I think it just depends on specific implementation. Generally, what you'll see, so if you're using a firewall for the purposes of authentication, which generally it'll be something like that, maybe there's some sort of encrypted passphrase that's included in the header. And then the gateway or the firewall itself can just kind of check that, use like a private key to make sure that it matches whatever hash it should, and then let the packet go through.
You can also have like matching by the fields, in addition to like security for the firewall for authentication.
Cool. So I guess I will stop the recording.